we're going to work some examples so that we can illustrate how we're going to apply the central limit theorem and how we're going to work with sampling distributions. So here's an example I like to use. It's about snakes. It reads, herpetologists found that a certain species of reticulated python have an average length of 20.5 feet with a standard deviation of 2.3 feet. One herpetologist fears that pollution might be affecting the natural growth of pythons. Our first part A of this question, simply asks us, what is the probability that a randomly selected python is 19.5 feet or shorter? Now this problem here is no different from what you did in the last lesson, what we learned in lesson 1 of module 3. But I like to do this one first so that we can show in part B how things are going to change. So let's go ahead and let's accomplish part A. Here's our normal model here that describes the lengths of the pythons. As you can see, I indicated that the standard deviation is 2.3 as it told us, and the mean right underneath the peak of the bell curve is 20.5 feet. Each tick mark, as you notice here, if you get your calculator out, is 2.3 feet away from one another. So we just put the standard deviation tick marks in, and 19.5 feet fits nicely right here to the left of 20.5 feet. So it looks like it's less than one standard deviation to the left. That is, 19 feet is less than one standard deviation to the left of our mean. So in order to get the probability, which is the shaded region right here, we need to convert our axis into a z-score. So we'll take our 19.5 feet, subtract off the 20.5, which is the mean, and divide by our standard deviation of 2.3. So I like to say and emphasize, it's always where did you stop along the horizontal axis and divide the curve and shade on one side or the other. So we did that at 19.5. You subtract off the mean, the middle, and you divide by the standard deviation. When you do that in your calculator, you will get a z-score of negative 0.43. The next natural step is to go to your z-table or possibly software and try to figure out what corresponds to a z-score of negative 0.43. Well, once you look it up, you'll discover that the solution is 0.3336. That is the area of the red region in our diagram. Now the area is synonymous with probability. So that means there's a 33% chance that a randomly selected python will be less than 19.5 feet long. So we could further simplify that and say 1 in 3 pythons will be less than 19.5 feet long. So again, that's what we did in our last lesson. Let's look at part B here and see how things are going to change when we work with sampling distributions. The scientists collect a random sample of 30 adult pythons and measure their lengths. In their sample, the mean length was 19.5 feet. Do you think the sample result is unusually small? So what's changed here is that the scientists didn't just select one snake. They actually took a sample of 30 snakes, 30 pythons, and let them be represented by their mean length. That is, they added all the snakes' lengths up and figured out that and divided by 30 and figured out that mean length was 19.5. So they're working with a collection of snakes rather than just one. So you can see the first thing that's different about this picture is the red region isn't near as large. And that's because we had to modify our standard deviation. This is the standard deviation of a sampling distribution of means. We have to take the original 2.3 they gave us and divide it by the square root of our sample size, which is 30. This works out for our standard deviation to be approximately 0.42 feet. Now it went from just under 2.5 feet to just under a half a foot. So you can see now that the tick marks are exactly 0.42 apart from one another. Now what I did next was figure out where 19.5 fits in this picture. fits right to the left of 19.66. Now we can see that it is 1, 2, and a little bit. So a little bit over 2 standard deviations from the mean. The z-score will tell us exactly how many. So again, I still have the same numerator. It's still 19.5 feet. Take away 20 feet, the mean. But now I'm dividing by 0.42. And that makes our z-score negative 2.38. As expected, just over 2 standard deviations away. We go and we look into our z-table, or software if you prefer, and it tells us that the area here, that little tiny region there, is 0.0087. Now let's convert that to a percent. We can make a meaningful statement. There is a 0.87% chance, that is not even a 1% chance, that 30 randomly selected pythons will have a sample mean less than 19.5 feet long. I would find this extremely surprising for a couple of reasons. The z-score is further than 2 standard deviations, or is less than -2, we like to say. Also, our probability is extremely small. Usually we say unusual happens at around less than 5%. You can clearly see this is less than 1%. So I think that the mean length of these snakes is unusually small. Would probably start to support the scientist's hunch that possibly pollution is stunting the growth of these snakes. At least it's a good place for him to start his research.